The James Webb Space Telescope, also known as Webb or JWST, is a scientific pioneer that has revealed incredible insights regarding stars, planets, galaxies, and other fascinating cosmic phenomena. It has set new standards for scientific robustness and is celebrated as the preferred successor to the Hubble Space Telescope. People worldwide are sharing images or using raw data to create new discoveries. Join us on this astronomical journey. Just 3 minutes ago, the James Webb captured the most astonishing image ever seen in history. It has been 365 days since the colossal James Webb Space Telescope unveiled its first memorable photograph of the universe, stunning stargazers globally with its extraordinary detail. Its latest discovery is an unprecedented image of the universe. What has been observed so far through the James Webb Space Telescope is raising more questions than it answers. As the replacement for the Hubble telescope, Webb has unveiled new data about star development, galaxy merges, and the early universe. Only 1 month after the initial images were released, the photos were remarkable, revealing the universe in breathtaking detail. Since then, the number of discoveries has soared, providing researchers with a vast treasure trove of data. James Webb Space Telescope observations of grandeur tarantulas, record-breaking space smokes, stars near their cosmic explosion blasts, and other astounding celestial objects have been documented. This satellite observatory's innovative technology allows us to peer farther into space than ever before, uncovering previously obscure details about the universe. A new era in cosmology has begun thanks to the detailed images captured during the first year of the James Webb Space Telescope's mission. NASA recently released an image showing a small star-forming region within the Rho cloud complex. The photo displays jets ejecting from young stars amid significant dust clouds of various colors. Atomic hydrogen makes up the red dust, and the presence of a circumstellar disk casts shadows on a few stars, suggesting the possibility of planet formation. Although the photo might appear to depict cosmic chaos, according to NASA, this stellar nursery is small and serene compared to others. Moreover, many young stars in this region are about the size of our Sun or significantly smaller, making it the closest star-forming area to Earth. This photo was captured by the observatory's primary camera, the Webb Space Telescope's near-infrared camera, which captures cosmic images in distinctive infrared ranges. Additionally, the Space Telescope has enhanced our understanding of exoplanets, or worlds that orbit stars other than our Sun. James Webb is particularly adept at observing large distant galaxies. The satellite observatory discovered its first exoplanet, LHS 475b, at the beginning of 2023. The planet is 41 light-years away and has a diameter comparable to Earth's. According to NASA, James Webb is the only operational telescope capable of analyzing the atmosphere of Earth-sized exoplanets. The researchers responsible for the discovery have demonstrated the telescope's precision. Studying exoplanets is now a new frontier for stargazers to explore. Recently, the James Webb Telescope found evidence of distant ancient galaxies that theoretically shouldn't have existed. The Evolution Laboratory at Swinburne University and its galactic organization have identified 6 enormous ancient galaxies known as universe breakers, which could potentially revolutionize our understanding of space. These colossal galaxies might have appeared between 500 to 700 million years after the Big Bang. The telescope's infrared sensors detected them, allowing us to look back in time around 13.5 billion years when stars and cosmic structures were much younger. The immense size of these universe breakers has astonished researchers. Galaxies in the early universe should have been 10 to 100 times less massive than these. Calculations indicate that these 6 objects could be billions of times heavier than our Sun, with the total mass of all the stars in one galaxy potentially being 100 billion times heavier than our Sun. The prospect of understanding something so colossal is daunting. Despite technological advancements, some remarkably large planets perplex specialists. One such finding is a planet considered excessively big for its Sun, leading to a reevaluation of our understanding of planetary formation and solar system architecture, as well as the models created by stargazers. A planet multiple times the size of Earth has been observed, according to research from Penn State. This planet exists in a planetary system around the extremely cool star LHS 3D1154, a star much less massive than our Sun. Before recently observing it themselves, researchers didn't believe such a scenario was possible. Yet new evidence suggests that the largest planet in our planetary system is orbiting one of the universe's smallest and coolest stars, an extremely cool dwarf. This finding demonstrates our limited understanding of the universe. A planet of this mass orbiting a star with such low mass challenges our assumptions. These stars might have formed in larger gas and dust clouds. Planets may emerge from the gas and dust that remain in the disk of material around the infant star. However, it wasn't expected that the planet-forming disks around the low-mass star LHS 3DY54 would contain enough solid mass to produce this planet. But it exists. Consequently, we must now re-examine our hypothesis regarding stellar and planetary development. An interesting comparison would be to liken the star to an outdoor fire. To maintain your internal warmth as its temperature decreases, you need to get closer to the fire. Planets are no different. Planets that need to be warm enough to support liquid water must be closer to their stars. You can use the inner planets of our solar system as a model to understand how planets become hotter the closer they get to the star. For example, Earth is in the middle of the habitable zone, receiving the right amount of water and heat from the sun. The distances of other planets from our sun are either too ideal or too small for them to receive the proper amount of light to support life. Now picture a universe with an exceptionally cold star like drawing closer to the campfire. Planets orbiting a cold star must do the same to get the optimal proportion of heat to support life. The radius of the planet must also be adjusted to find the ideal distance for heat and light to support life. Returning to our previous discussion, there are various theories as to why the planet may have formed near the small star. According to one commonly held belief, the planet could have been significantly larger initially. Over time, it might have lost a substantial portion of its mass. However, this hypothesis has a major flaw since losing mass makes a planet lose more gas than solids. In this case, it's assumed that most of the planet's mass would have been gases, which conflicts with the findings. Another explanation is that this large planet formed far from the tiny star. If the planet had maintained its distance from the low-mass star without receiving much light, it might be ice-covered. The star could eventually gravitationally attract this distant planet, resulting in this significant planet being close to the tiny star. Although both ideas could explain the peculiar planet-star pair, researchers are still unable to conclusively make sense of the phenomenon at this time. With cutting-edge advancements like the JWST, scientists are now examining planetary systems in greater detail, and each new discovery pushes them further. We've learned more about how the universe has formed in recent months than we have in the past 30 years. The immense amount of data that the telescope provides has already led to significant scientific advances, surprising stargazers and stirring up interest in future space exploration. With the James Webb Space Telescope operating for a year now, one thing is clear: the universe is significantly more complex than we previously believed, and there are numerous questions that we are yet to answer. The James Webb Space Telescope, JWST, has opened new frontiers in space exploration and astronomy, making groundbreaking discoveries that challenge our understanding of the universe. Its advanced technology allows it to peer deeper into space than ever before, capturing images and data with unprecedented clarity and detail. This has led to significant advancements in our knowledge of star formation, galaxy evolution, and the fundamental properties of the universe. JWST's ability to observe in the infrared spectrum has been a game-changer. Infrared light can penetrate dust clouds that often obscure objects in visible light, revealing hidden regions of space. This capability has allowed JWST to study star-forming regions with exceptional detail, providing insights into the early stages of star development and the processes that lead to the formation of planets. For instance, the telescope's observations of the Tarantula Nebula, a massive star-forming region, have uncovered thousands of young stars and the complex interactions of gas and dust that drive their formation. Another significant contribution of JWST is its study of exoplanets. The telescope's instruments can analyze the atmospheres of these distant worlds, detecting molecules such as water vapor, carbon dioxide, and methane. This ability to characterize exoplanet atmospheres is crucial for understanding their potential habitability and the diversity of planetary systems. One of the notable discoveries is the detection of LHS 475b, an Earth-sized exoplanet located 41 light-years away. By analyzing the light passing through the planet's atmosphere as it transits its star, JWST can infer the atmospheric composition and search for signs of life. JWST's observations have also provided new insights into the early universe. By looking back in time to when the first galaxies formed, the telescope has captured images of galaxies that existed just a few 100 million years after the Big Bang. These early galaxies, sometimes referred to as universe breakers, are much more massive than previously thought possible for that era. This challenges existing theories of galaxy formation and suggests that galaxies may have formed and evolved more rapidly than previously believed. The data from JWST is prompting astronomers to revise their models and explore new theories to explain these observations. In addition to studying distant galaxies and exoplanets, JWST has made significant contributions to our understanding of the Milky Way and its neighbors. It has provided detailed images of the Andromeda Galaxy, revealing its structure and the distribution of its stars and dust. These observations help scientists understand the dynamics and evolution of galaxies similar to our own. Another intriguing area of study is the interaction between stars and their planetary systems. JWST has observed planetary systems where large planets orbit very close to their stars, defying current models of planetary formation. These hot Jupiters challenge our understanding of how planets form and migrate within their systems. The discoveries made by JWST in its first year of operation highlight the telescope's transformative impact on astronomy. The detailed images and data it provides are not only expanding our knowledge, but also raising new questions and opening up new areas of research. The telescope's ability to observe the universe in unprecedented detail is revolutionizing our understanding of the cosmos and paving the way for future discoveries. As JWST continues its mission, astronomers anticipate many more groundbreaking findings that will further our understanding of the universe and our place within it. This technological marvel has enabled us to look further back than ever before, capturing the light from the earliest galaxies that formed shortly after the Big Bang. By observing these ancient galaxies, JWST is helping scientists understand the conditions and processes that led to the formation of the first stars and galaxies, shedding light on a period of cosmic history that was previously shrouded in mystery. One of the telescope's most remarkable capabilities is its ability to measure the chemical composition of celestial objects. By analyzing the light spectra of stars, galaxies, and exoplanets, JWST can identify the presence of various elements and molecules. This information is crucial for understanding the physical and chemical properties of these objects, as well as their evolution over time. For instance, by studying the atmospheres of exoplanets, JWST can detect signs of potentially habitable conditions, such as the presence of water vapor or other biomarkers. JWST's high-resolution imaging and spectroscopic capabilities are also allowing scientists to study the detailed structure and dynamics of galaxies. This includes observing the distribution of stars, gas, and dust within galaxies, as well as the interactions between galaxies. These observations are providing new insights into the processes that drive galaxy formation and evolution, including the role of dark matter and the impact of galaxy collisions and mergers. By understanding these processes, scientists can better comprehend the large-scale structure of the universe and the forces that shape it. In addition to its contributions to the study of distant galaxies and exoplanets, JWST is also enhancing our knowledge of objects within our own solar system. The telescope's ability to observe in the infrared spectrum makes it particularly well-suited for studying cold and distant objects, such as the outer planets, their moons, and small bodies like asteroids and comets. These observations are helping to answer fundamental questions about the formation and evolution of our solar system and the processes that govern its dynamics. JWST's discoveries are not limited to the distant past or faraway galaxies. The telescope is also providing valuable data about the interstellar medium, the space between stars filled with gas, dust, and cosmic rays. By studying the interstellar medium, scientists can learn about the life cycle of matter in the galaxy, from the formation of stars and planets to their eventual destruction and recycling. This research is crucial for understanding the complex interactions that govern the behavior of galaxies and the universe as a whole. JWST's ability to observe faint and distant objects has also led to the discovery of previously unknown phenomena. For example, JWST has detected new types of variable stars and transient events, such as supernovae and gamma-ray bursts, which are providing fresh insights into the life cycles of stars and the violent events that can occur in the universe. These discoveries are helping to fill in gaps in our understanding of stellar evolution and the mechanisms that drive these powerful explosions. Another exciting aspect of JWST's mission is its potential to address some of the most profound questions in cosmology. For instance, by studying the distribution and behavior of dark matter and dark energy, the telescope is helping scientists unravel the mysteries of these elusive components of the universe. Dark matter and dark energy together make up about 95% of the total mass energy content of the universe, yet their nature remains largely unknown. JWST observations are providing new clues about how these mysterious substances influence the formation and evolution of cosmic structures. The telescope's ability to capture high-resolution images and spectra of distant objects is also contributing to our understanding of the reionization epoch, a critical period in the early universe when the first stars and galaxies ionized the surrounding hydrogen gas. This process marked the end of the cosmic dark ages and the beginning of the universe as we see it today. By studying the sources of reionization and their impact on the intergalactic medium, JWST is helping to piece together a more complete picture of this transformative era.